In this video, we are going to study concept of frequency response and impulse response. So as we know that impulse response of a system is given by y of t equal to x of t convolving with h of t, where this h of t is the system transfer function or the impulse response of the system. So we obtain y of t as the output of a system when we apply x of t to a LTI system whose impulse response is h of t and output is y of t. So y of t will be equal to x of t convolving with h of t, that is the impulse response. Now we are supposed to find out the frequency response. So let us take the Fourier transform of this equation. So we have take Fourier transform. To take Fourier transform, here we have convolution. So we have the convolution property of the Fourier transform as y of t will be represented as y of omega equal to x of t will be represented as x of omega, and now convolution will be replaced by simple multiplication into h of omega. So if we rearrange this equation, we get h of omega equal to y of omega upon x of omega. This equation is called as the frequency response. And from this frequency response, if we want to find out the impulse response, we need to take the inverse of the frequency response. So if we take inverse Fourier transform of this equation, we get, for h of omega, we will get h of t, which will be the impulse response. So let us take a simple example. Find the impulse response for the following system, and the system is defined by a differential equation. So the equation of this kind, like d by dt of y of t plus 2y of t equal to d by dt of x of t plus x of t. So if you have such kind of equation, these equations are called as differential equations. And now from this differential equation, we are supposed to find out impulse response. So to find out impulse response, first of all, we need to find out frequency response. So ultimately our aim is to find out h of t. So let us take Fourier transform on both sides of this equation. So we have the Fourier transform of d by dt of y of t as, so here using the time differentiation property, d by dt of y of t will be j omega into y of omega plus 2y of omega equal to j omega into x of omega plus x of omega. Now simplify this equation. So we can take y of omega common, and the remaining term will be j omega plus 2 equal to, and here also take x of omega common, so the remaining term will be j omega plus 1. So if we take the ratio of y of omega divided by x of omega, this term will be equal to j omega plus 1 divided by j omega plus 2. So we have obtained y of omega upon x of omega, which is nothing but, this equation is nothing but h of omega, which is the frequency response. Now we need to find out the impulse response, so we need to take its inverse. So here we have the two polynomials, so we can just make an arrangement such that in the denominator we have j omega plus 2. So in the numerator we'll just do certain arrangement so that we can simplify this equation. So this equation h of omega will be equal to, so in the denominator I have j omega plus 2. If it is normal quadratic equation, then you can go with the partial fraction expansion and you can find out the inverse. But here it is simple example, so we just do a certain arrangement and we get the answer. So j omega plus 2 minus 1. So in this way we get the resultant as j omega plus 1 itself. So here let us separate out the terms. J omega plus 2 upon j omega plus 2 minus 1 upon j omega plus 2. We have just separated out these terms. So the first term will be 1 minus 1 upon j omega plus 2. This is our h of omega. Now we need to find out the inverse of this equation. So to find out inverse, here we have 1 and here we have 1 upon j omega plus 2. So we have the standard equations. The impulse function, its Fourier transform is 1. So if we take inverse of 1, we get function delta t, and e raised to minus at ut, its Fourier transform is 1 upon a plus j omega. So use these two identities and find out the inverse for h of omega. So this h of omega, so take inverse Fourier transform on both sides. We get h of omega will be replaced with h of t equal to inverse Fourier transform of 1 is delta t minus, as it is, 1 upon j omega plus 2. So it will be e raised to minus 2t into u of t. So this will be the impulse response for the given example. So to summarize, a differential equation was given. So using this differential equation, we go with the Fourier transform. So we rearrange the terms to get y by x equation in terms of omega. Then whatever equation we are getting for the y of omega by x of omega, that equation is nothing but your frequency response. So take the inverse of this equation using partial fraction expansion or the simplest way of rearrangement, you will get the impulse response for the given frequency response. Remember, impulse response is in time domain and frequency response is in frequency domain. So this is how we can solve the examples on the differential equation or frequency response and impulse response.